Okay, hi everyone. My name is Yuan Shangguan, the first author of this paper, and my team is a Google Speech on-device speech team. And so today I'm talking about optimizing speech recognition for the edge devices. And I know not many people are from speech here, so just a little bit background on the model. So the speech model that we have developed over the past 5 years of investment is an end-to-end audio in, transcription out model. Traditionally, in a speech model, you will contain a language model that models the linguistic context, and then you have an acoustic model that models the acoustic context. But in this end-to-end model, you kind of combine these two models together. So on the right, the encoder is essentially analogous to an acoustic model. And on the left, a predictive network takes in the previously emitted label and then predicts the next label. So it functions like a language model. And you train them by concatenating the upper layer level into a joint network and then put it into a softmax. So then you can predict the next label. And so the model that we use is basically 8 layers of LSTM as a baseline model in the encoder, 2 layers of LSTM similar to the language model just presented just now, and the joint layer for us is just a simple DNN layer. This model is actually pretty good, and it's now in a lot of Android devices. A lot of you might be using them offline. And the motivation here for us is really to produce an even smaller model that can run on a very simple CPU chip, although our techniques can also be used on advanced chips like TPU and neural processing units as well. So not only to we want a smaller storage for the model. We want to keep the runtime latency very, very low on the CPU. And also we want a very, very small degradation in the word error rate, which measures the model quality in speech. So eventually this paper presents a combination of 3 techniques that shrinks the model parameter down to 40% and shrinks the size of the model down to 12%. So that's about 7.9 compression ratio. And so why I think this is interesting to you guys is because shrinking RNT is not a trivial task. You're not just processing one single cell or one single layer. You're actually looking at a combination of interactions between the different components. For example, techniques that you use on your encoder may not necessarily speed up the model because you have multi-threading and then your decoder or your language model is waiting for your encoder. So in this framework, we want to just talk about the 3 techniques. We start with pruning. So sparsification is one of the commonly talked about technique in this conference. We use block sparsity, and it measures the number of 0 blocks divided by the total number of blocks in the matrix. So an example here shows that 2 times 2 block sparsity is 25%, whereas 1 times 1 random sparsity is a little higher. And another topics on sparsity is how you actually sparsify your model. What's the schedule you use? There's a lot of hypotheses out there, lottery ticket hypothesis for sparsifying schedule. We actually choose to train directly from scratch using a polynomial increasing schedule that is actually previously introduced by Suyok and Michael. So this schedule basically ramps up the sparsity to the desired level from 0 over a period of time. And one of the things that we found very, very useful, we want to emphasize here, is that we actually retain the previously pruned weights. And once you have some other blocks that the weights of which drop below the previously pruned weights, we resurface those weights. So you can see the red block here. After we find the weight pruning, the red block is being frozen. And so it's not participating in backward or forward propagation. However, later when you have another red block on the extreme right, another red block that falls below this average pooling value, we resurface the block from the previous values. This has been extremely helpful in maintaining model accuracy in the midst of pruning. Another technique that we use is less talked about here is about swapping your LSTM cells with alternative cells. A lot of experiments in other conferences have talked about alternative cells. If you examine the LSTM cell, it's pretty dense. Each gate, input gate, forget gate, output gate, you have the recurrent matrices, you have weight matrices. So one of which we experimented with is really to couple the input and forget gate. So that's called CIFG, couple input gate, forget gate. You use the same set of weights to control the two gates. So essentially the intuition here is that the cell should learn the same amount of information as 1 minus the content that they should forget. So by simply doing so, we reduce like 1/4 of the parameters. And another thing that we tried is called simple recurrent unit. So you see the red marking here is that it gets rid of the recurrent matrices. So this move is very important because of two factors. One, that you reduce almost half of your parameter. The second one is that you reduce the dependency on the previous hidden value output, the H, which means that now you can parallelize all this computation of the different X1, X2, and forget gate and reset gate. So that will help you speed up the model a lot. One of the important things that we learned is that for a speech model, a more complex system, simply swapping every cell to the same cell is not enough. If you use SRU everywhere in the model, you're going to have a severe model accuracy degradation. However, we found that only swapping part of the model, like in the predictive network, the decoder, it's very, very helpful. And the model accuracy still stays about the same. And last but not least, we rely on quantization to shrink the model and to make it go faster. So the hybrid quantization is implemented in a way that your activations are still preserved in the floating point accuracies. An integer quantization that we use basically compute a whole graph in integer level. So one of the tricks that we have in our speech system is called layer normalization. So in each layer, all the weights of the same gates gets normalized, denormalized to 0 mean and 1 standard deviation. So that implication is that most of your weights will be within the region of 1 sigma, right? So that means 97 of the weights will be -3 to 3. So that only has 7 bits of representation. In order to avoid this restriction, we added a weight value to the layer normalization weights, and that solved our problem. So eventually, this is our kind of like the grand chart of the results. Let me just explain a little bit. On the y-axis, you have the model accuracy measured by word error rate. On the x-axis, you have runtime factor, which is measured by how much time is being taken divided by 1 second of audio. So the smaller, the better. And if it's falling below 1 second, means that your model is running in real time. You're getting that transcription in real time. So ideally, you should fall within this section. So we started from the dense LSTM flow from the extreme right. And as we swap the CIFG, you can see the accuracy degraded and the model gets smaller. We quantized them even more and added SRU to actually boost the accuracy. And so eventually we arrive at one of the best models, and it's now on Google Home. Thank you, and you can ask us any question here or later at a poster. Thank you.
Nick Lane, Oxford. Just super quick question. Is that y-axis, what data set is that? Is that library speech or something? Or?
I'm sorry, this is not a library speech because it's a production model. So this is actually a voice search data set.
So it's your own data set?
Yes, it's our own data set. But we do have the same setting on library speech, and we will publish that in the future conferences.
Okay.
Yeah.
Thanks.
Mm-hmm. Thank you.